Hey, this is Physics Unit 3, video number 3, and today we are beginning on the back of page 2. So we've been looking at adding vectors together, finding the sum or resultant vector. Today we are going to be doing the same thing. We are adding two velocities. So we're going to get two separate velocity vectors. First off, we have an airplane heading 30 degrees north of west. So I'm going to draw, here's north and south, and here is east and west. This is our basic map coordinates that we'll be using in this class. 30 degrees north of west at 300 miles per hour and encounters a 25 mile per hour wind out of the northeast. Find the resultant velocity of the plane, and there's a note here, draw a sketch first. In physics, we pretty much always want to draw a picture first. It's going to help to figure out what's going on. It's just going to make a huge difference. So first thing, method 2, I'm not going to get into much, so if you want to use most of this whole area, it's going to be fine. You can do that. So, all right, here is our basic grid coordinates, and everything is kind of going off in this direction, so that's how I'm going to draw it. All right, the first vector that we get is an airplane heading 30 degrees north of west. So 30 degrees north of west, so here's west, this would be going north of west. So this angle here is about 30 degrees, and it's going at 300 miles per hour. So here's 300. For now, I'm going to leave out the angles to keep this picture simple. We're going to draw a few more pictures as we go through this problem. It encounters a 25 mile per hour wind out of the northeast. So here is the northeast. Out of the northeast means it's coming in this direction. So it is actually blowing towards the southwest. Northeast coming in. This vector is 25 forward. There we go. 25. And so we're going to draw the sum vector. So let's do our parallelogram method. Something like that. The picture doesn't have to be perfect. We are basing our calculations off of the numbers. The picture is just to help us see what's going on. And there's the sum. Okay. Some things that we know that this airplane is going at 30 degrees north of west. We know that the wind is coming out of the northeast. When it says something like that without giving an angle, you can assume that this is going to be 45 and this is going to be a 45. So it's exactly between the west and the south. So in order to do this a little better, we need to draw a couple of triangles. So we have to look at each of these vectors in terms of the i's and the j's. We have to figure out the horizontal component and the vertical component of the airplane. We need to know the horizontal and the vertical of the wind. So here's what we're going to do. We're going to draw some triangles. There's going to be some trigonometry here. We're going to use SOHCAHTOA. In case you haven't heard of SOHCAHTOA or you forgot, it means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Maybe we'll write that in here. Opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So this is going to be really important concepts really throughout the next couple of units. We're going to need them a lot. So familiarize yourself with this. All right. So the first thing I'm going to do is look at the airplane. So the airplane is heading at 300 miles per hour, and we know that it is 30 degrees north of west. So what we can do is make a right triangle here, and this allows us to use our SOHCAHTOA. So the horizontal component is the I, the vertical component is the J. We need to know the speed in the horizontal component. We need to know the speed in the vertical component. So here's basically what we're looking for. Plane, 300 miles per hour, 30 degrees north of west. So we need to know the I component, and we need to know the J component, horizontal, vertical. So this is what we're looking at. So when we want to know, let's go for J first. So we have an angle, we have a hypotenuse. This one is going to be the opposite. So for J, we have opposite over hypotenuse. That's going to be sine. So J is sine of 30 degrees equals the opposite over the hypotenuse. When you're doing these problems, if you want to save a little bit of work, the first step that you can do, you can jump right to this. J equals 300 sine of 30 degrees. So if you show no other work, this is the step that I should see. But this one shows you how I got there. And so we find that J equals 150, and that would be in terms of miles per hour. So this is J, and we are going towards the north. Towards the north is going to be positive, towards the south is going to be negative. So for this one, we have 150. The horizontal component, we're going to use the same triangle. So for I, here's our angle, here's our hypotenuse. This is the adjacent side. So we have a hypotenuse and adjacent. We're going to use cosine. The cosine of 30 degrees equals I over 300. Again, your minimum step for showing your work, I equals 300 cosine of 30 degrees. And we find the horizontal component equals, write it off here. The horizontal component, 259.8. Direction is important here. So on a standard map coordinate system, going to the right makes something positive, going to the left makes it negative. So going to the east will be positive, going to the west is negative. So this number, 259.8, the horizontal component, is negative because it is going to the west. That negative is showing us the direction. Let me label this. This one was for the plane. I'm going to box it off. Box it off so we can keep our work separate. And there it is. The next thing we have to look at is the wind. The wind is moving at 25 miles per hour and it is out of the northeast, but it is going to the southwest. And so we look at the horizontal component and the vertical component. We're going to draw another triangle. So we've got a triangle just for the plane's velocity. We have a triangle just for the wind. So here's what the wind looks like. We know that it is headed to the southwest and it's 25. So it is going down. That's our vertical. And it is going west, which is our horizontal. Again, this is a right triangle. And since the southwest or out of the northeast didn't specify exactly what the angle was, in this situation we can assume that it's going to be 45 degrees exactly. Let me see if I can. .45 and then 45. There we go. So this one I'll label. This is the wind. So we want to find the horizontal and the vertical components. So last time I kind of went out of order and did vertical first. I'll do the horizontal first this time. For the eye. Here is the eye. So let's use this angle up here since this one is really showing us. So using this angle, we're talking about eye is opposite and 25 is the hypotenuse. So opposite and hypotenuse is sine. So sine of 45 degrees is I over 25. And so this would be your minimum work step. I equals 25 sine of 45 degrees. And we find that I equals 17.7. And if we were to do J, it would be the same thing really. You could start with this angle and do opposite over hypotenuse. It would be J equals 25 sine of 45. So these are actually equal. So for the wind, we come back up here. We know that our horizontal component is 17.7. And remember, it is moving to the west or to the left, which makes it negative. The vertical component is also 17.7, and it is going down towards the south. So this one would also be negative. So if you're looking at your map coordinates, basically north is, what is a different color, going to be positive. East is going to be positive. South would be negative, and west would be negative. So then we can find the sum of these vectors. So sum equals, here's the horizontal component, here's the vertical component. And so basically what we do is just draw a line here and add everything together. So negative 259.8 plus negative 17.7. The total of the horizontal components is negative 277.5. And the total of the vertical components, 150 plus negative 17.7. We have 132.3 for the J's. So now we have some information, excuse me, for the sum vector. This information is something we're going to use to draw a third triangle. So let me separate this one off. And I'm going to erase our SOHCAHTOA. Hopefully you had time to write it down, or hopefully you remember. So we are drawing this sum vector. So if we look at the horizontal component, it is negative, which means the horizontal component is going west. So let's draw this on a coordinate plane. Yeah. So we know it's going west, and this is positive. The vertical component is positive, so we know it's going north. So I'm going to draw, here's my coordinate plane. It's going negative 277.5 horizontally. That is west, 277.5. And then it's going, the vertical component is 132.3. Positive means it's going north. So there's 132.3. This is a west, this is a north, that makes a right triangle. And so we're going to draw the sum vector, or the resultant vector. This board just doesn't work. There we go. Here is the sum vector, and this is going to be the direction. It's theta right now because we don't know the exact direction, but given two sides of a triangle, we can figure out the third, and we can figure out the angle. So since it is a right triangle, we can use the Pythagorean theorem, a squared plus b squared equals c squared. So I'm going to write sum squared equals 132.3 squared plus 277.5 squared. And just writing that, skipping all the work being written down. The sum equals 307.4, and this is in terms of miles per hour, because the original velocity vectors were miles per hour. for theta, we have an opposite side and we have an adjacent side, which would be tangent. So if we said tangent of theta equals the opposite, 132.3, over the adjacent, 277.5, we would take the inverse tangent and we find that theta equals 25.5 degrees. And so finally, our answer, let me box this up too. Maybe I'll even number them in the order. So we went 1, 2, 3, and 4. So we can write our summary here, and the sum is 307.4 miles per hour at 25.5 degrees, and this angle is north of west. North of west. Method 2, like I said, I wasn't really going to get into it much. Method 2, I'll just draw a line over here. I'm not going to teach this. I'm not a math teacher, so I probably would just end up confusing some people. Use method 1. But method 2 is doing this problem using the law of cosines. If you're familiar with the law of cosines, you can think about it. Otherwise, just stick with method 1. This is the way that you should do most of your physics anyway.